Hello and welcome everyone to our weekly session titled Latest in Bitcoin Tech, where we go through the weekly Bitcoin Optech newsletter. And this week we will go through newsletter 324 published on 11th of October 2024. This week we have the news section like we do every week, which covers three news articles. One is basically a guide for wallet developers, and two are news articles that deal with vulnerabilities. The first news article covers past vulnerabilities that affected Bitcoin Core, and the second news article covers a vulnerability that affected btcd, which is another implementation of Bitcoin. Then we have a review club that we will go through and see what this PR does, and then release and release candidates and notable report and documentation changes. Well, let's go to the preface in brief to understand what the news article contains. This week's newsletter announces three vulnerabilities affecting all versions of the Bitcoin Core full node. Announces a separate vulnerability affecting all versions of the btcd full node, and links to a contributed Optech guide describing how to use multiple new P2P network features added in Bitcoin Core 28.0. Also included are our regular section summarizing a Bitcoin Core PR review club meeting, announcements of new releases and release candidates, and descriptions of notable changes to popular Bitcoin infrastructure software. All right, let's commence with the first news article, which is titled Disclosure of Vulnerabilities Affecting Bitcoin Core Versions Before 25.0. Nicholas Kauger posted to the Bitcoin Dev mailing list links to the announcements of three vulnerabilities affecting versions of Bitcoin Core that have been past their end of life since at least April 2024. Give me a second. All right, so these are three vulnerabilities that affect Bitcoin Core's version 25.0, versions before 25.0. Okay, versions before 25.0, the latest one being the latest version being 28.0. What's the first vulnerability? Remote crash vulnerability. An attacker can send a compact block message deliberately designed to fail block reconstruction. Failed reconstructions sometimes happen even in honest use of the protocol, in which case the receiving node requests the full block. However, instead of replying with a full block, the attacker could send a second compact block message for the same block header. Before Bitcoin Core 25.0, this would cause the node to crash, as the code was designed to prevent the compact block reconstruction code from running more than once on the same compact block session. This is easily exploitable vulnerability. This easily exploitable vulnerability could have been used to crash any Bitcoin Core node, which can be used as part of other attacks to steal money from users. For example, a crashed Bitcoin node would be unable to alert a connected Lightning node that a channel counterparty was attempting. The vulnerability was discovered, responsibly disclosed, and fixed by Nicholas Kauger with the fixed release in Bitcoin Core 25.0. Okay, so this news article talks about a vulnerability that Bitcoin Core's versions prior to 25.0 were susceptible to. Okay, and as we have discussed in previous sessions, that there are certain protocols that need to be adhered to while disclosing vulnerabilities, and that is why when the affected Bitcoin Core clients have gone end of life, okay, so when they are beyond maintenance, when they are end of life, that is when this vulnerability was released, to ensure that either none of the clients are impacted or the clients impacted are very little, provided they have not upgraded despite receiving adequate warnings. What is this vulnerability about? We know what compact blocks are. Okay, in brief, just in case there are new joinees, what's a compact block? A compact block is nothing but a Bitcoin block that contains the compact versions of Bitcoin transactions. What's a Bitcoin block? A Bitcoin block is nothing but an amalgamation of transactions, right? It has some metadata, but primarily all it contains is transactions. In what format do those transactions exist in the Bitcoin blockchain? They don't exist in human readable format, meaning they do not exist in the form of JSON objects. They exist in the form of TXIDs. So you take a Bitcoin transaction, you double hash it, you subject it to a SHA-256 algorithm that gives you a 32 byte output, and that output is known as the TXID, or the transaction ID, using which a transaction is referenced on the blockchain. And those TXIDs are the main constituents of a Bitcoin block. Okay. Now, what is the compact block? The compact block does not use the output of a SHA-256 algorithm to identify a transaction like the regular blocks do. Okay. So if you go to a Bitcoin blockchain explorer and you look at any block, you'll see that the block is full of transactions. And if you look at those transactions are referenced or identified on the network by their TXIDs, or their transaction IDs, which are nothing but 32 byte outputs of a SHA-256 algorithm. But what is a compact block? In compact block, unlike regular blocks, the transactions are not identified by the TXID. They are identified by what is known as short TXID, or short identifiers, which are 6 bits in size. 6 bits, I believe. Do I have that compact blocks? I think it's 6 bit. 6 byte, I'm sorry, 6 bytes. So a regular block represents in 32 bytes, whereas a compact block represents in 6 bytes. So you subject the transaction to a different cryptographic hash, not to a SHA-256 algorithm, because a SHA-256 algorithm gives you a 32 byte output. So you subject the transaction to a different cryptographic algorithm that gives you a 6 byte output. So in a compact block, the transactions are referenced by 6 byte outputs. Now, what this does is that when you have less data to relay over the network, it reduces the bandwidth consumption, and it reduces the latency as well. So what happens is that you have certain peers which are compact block peers. Okay, you have inbound peers, you have outbound peers, etc. You have different kinds of peers. So there are certain handpicked peers that you pick and you choose them as your compact block peers. What these peers do is that the moment a miner finds a block and the miner announces that block, these peers will send you compact blocks. So these peers will not send you blocks with entire transactions, meaning the 32 byte representation of a transaction. They will send you compact blocks with 6 byte of transactions. Okay. And because the data that they are sending you, because the block that they are sending you is compact, it reduces the latency and the bandwidth consumed. So block propagation is quicker. What happens is that once you've received the compact block, you look into your mempool. You look into your mempool and you start hashing the transactions that are in your mempool, and you start matching those transactions with the transactions that are in the compact block that your peer has shared with you. And if your nodes default policies are not drastically astray from what most nodes on the network are running, then you will have 98 to 99% transactions already in your mempool. So if a block is found, on an average, 98 to 99% of the transactions that are included in the block are already in your mempool. So all you have to do is subject those transactions to the same cryptographic hash, convert them into 8 byte identifiers, and then compare them with the 6 byte identifiers, and then compare them with the 6 byte identifiers that you have in the compact block. And once they match, then you substitute the 6 byte identifier in the compact block with a 32 byte transaction ID, and that is how you reconstruct block. That is known as reconstruction of blocks. And just in case if you don't have any transactions in a mempool, if there are some transactions, let's say, that are non-standard or do not abide by your node's policies, and they were included by the miner in a block that got mined, then you can ask your peer for that specific transaction, and then that peer will send you that individual transaction, which you can then include in the block. And so this process is known as block reconstruction. When you receive a compact block, you hash the transactions in your mempool and start reconstructing that compact block and turn it into an actual block, which you can append to your already existing blockchain. Okay, so I thought giving a pretext of what a compact block is, what block reconstruction is, and how transactions are represented in a compact block, so that we can understand the impact of this vulnerability better. Now let's read what this vulnerability exactly is. I will zoom a little. So when receiving a block announcement via compact block message, Bitcoin Core attempts to reconstruct that announced block using the transactions in its own mempool as well as other available transactions. If reconstruction fails due to missing transactions, it will request them from the announcing peer via a get block transaction message. In response, a block transaction message is expected, which should contain requested transactions. Okay, so the moment a block is announced and a peer shares a compact block with you, you immediately start looking into your mempool to see if the transactions that are included in the block that was just now mined are available in your mempool. And if they are available in your mempool, you start reconstructing that block with the transactions that are available in your mempool. Now, there is also a possibility that the block that was mined contains transactions which are not available in your mempool. The reasons could be many. Okay, in that situation, what do? Request the peer that shared the compact block with you for that specific transaction. So you tell them that, hey, 99% of the transactions that you sent me in this compact block are available in my mempool, but there are these set of transactions which are not available in my mempool. So you send me these transactions, okay? And then your peer will send you those transactions. So you send them a message saying get block transaction, that hey, I want these transactions. I don't have all the transactions with me to reconstruct the block. These transactions are missing from my mempool. Give me these transactions, which is conveyed with this RPC command. Then your peer will reply back using this RPC command, block transaction. So they will send you transactions. Okay. Now there's latency in the network. So when you send a get block transaction message and you request your peer for the transactions that are missing, you have to wait till the peer sends you those transactions. Okay. So there is latency in exchanging these messages. Let's read further. The compact block protocol employs shortened transaction identifiers to reduce bandwidth. We've discussed this. These short IDs are 6 byte in size, resulting in a small chance for collision, that is, transaction A has the same short ID as transaction B upon block reconstruction. Collisions will be detected as the Merkle route computed from the reconstructed set of transactions will not match the Merkle route from the block announcement. Peers should not be punished for collisions as they may happen spuriously, therefore they are handled by falling back to requesting the full block. So it is possible that a peer of yours might send you two transactions with the short IDs, okay, a collision, because eventually these 6 byte short IDs are a byproduct of nothing but a hash function, okay, even though the possibility is very meager, but just in case your peer shares you two IDs, two short IDs that are exactly the same. So it shares transaction A with you and transaction B with you, which have the same short ID, okay. And in this situation, what will happen is that your Merkle route will not match with the Merkle route of the block that was announced. Your Merkle route will not match with the Merkle route that you've announced. Okay, so this is known as a mutated block. So any block, any Bitcoin block that has two transactions with the same transaction ID, or any compact block that has two transactions with the same short ID, it's a mutated block. It is a mutated block. It's an invalid block. In this situation, what will happen? Bitcoin Core will create an instance of partially downloaded block whenever a new compact block is received. If missing transactions are requested, the instance is persisted until the corresponding block transaction message is processed. Upon receiving the block transaction message, partially downloaded block fill block is called, attempting to reconstruct the full block. In the collision case described above, the full block is requested, but the partially downloaded block instance as well as other state related to the underlying block request is left untouched. This leaves room for a second block transaction message for the same block to be processed and trigger fill block to be called again. This violates the assumption documented as an assert statement that fill block can only be called once and causes the node to crash. Okay, so what can happen is that when you receive a block, okay, when you receive a compact block and then you ask your peer for the missing transactions, there is an instance known as partially download block. Okay, so Bitcoin Core will create an instance of partially downloaded block. This is a state. I believe this is a class in Bitcoin Core. Okay, this is a class in Bitcoin Core. This is a data type basically. Okay, so when you are trying to reconstruct a block, okay, this class or this data structure, its instance is created, meaning your software is made to believe that you are constructing that block. you are constructing that block. If missing transactions are requested, the instance is persisted until the corresponding block transaction message is processed. So the moment you request for the missing transactions, your node is notified that you are now reconstructing a block, and your node is still in that state till you get all the missing transactions from your peer, and those transactions are processed and they are all valid transactions. Okay, until that you are still in this state. Upon receiving the block transaction message, partially downloaded fill block is called, attempting to reconstruct the full block. In the collision case described above, the full block is requested, but the partially downloaded block instance as well as the other state related to the underlying block request is left untouched. Okay, so if you're not able to reconstruct a compact block because of collision, what will you do? You'll ask for the entire block. Okay, you'll not ask for missing transactions now, because you ask for missing transactions and those transactions has had ID collisions, okay, due to which you had a mutated compact block. So what will you do? You will now not ask for individual transactions, you will ask your pay for an entire block. Meanwhile, your node is still in this state. Your node is still believing that you are reconstructing that compact block, whereas you have abandoned reconstructing that compact block and you have asked your pay for an actual full block. But your node is still in this state. Okay, this state is abandoned. Now you cannot trigger the state twice. Okay, the way the code was written is that you cannot trigger the state twice. Now what happens is that uh, this leaves room for second block transaction message for the same block. So your peer can send you another block transaction message. Your peer can send you another block transaction message. When your peer sends you another block transaction message, this fill block, which is an instance of partially downloaded block, gets triggered again. When this gets triggered again, your node crashes because it's an assert statement which fails. So your node crashes. Okay. So basically, what used to happen is that when you're constructing your compact block, your node went into a state, this state, okay, thereby declaring that your node is reconstructing a compact block. But when the reconstruction fails for any reason, and in our example could be collision of the short IDs, you will ask your other peers for the full block, okay, for the full block. In the meantime, if another get block transaction is sent to your node, another block transaction message is sent to your node, this fill block instance will get triggered twice. And the code was written in such a manner that you are only allowed to trigger this message once. And if it's triggered twice, there's an assert clause that fails. There's an assert clause which fails and your node crashes. Okay. So this was a vulnerability. What was this vulnerability? That if your peer sends you a compact block and there are transactions in that compact block which are not available in your mempool, you will ask your peer for individual transactions. When your peer shares you those individual transactions with the block transaction message, and you're trying to reconstruct that block and the reconstruction fails for some reason, you will request your peer for the full block. In the meantime, if you receive another block transaction message, then your fill block or the state will get triggered again for the second time. If the state gets triggered again, your node crashes. So this was a vulnerability. Now this vulnerability has been fixed. Time will not permit us to look into the actual PR, but how the vulnerability is fixed is that this assert clause is not triggered. So now you can trigger this instance fill block multiple times. So for a single compact block, you can receive multiple block transaction messages, and this fill block instance can be triggered and initialized on multiple occasions, and your node will not crash. So this is what the vulnerability was, and it's been fixed now. Right. So any questions pertaining to this specific vulnerability? Right. And like a nice observation here is that, for example, a crash core node would be unable to alert a connected Lightning node that a channel counterparty was attempting to steal funds. Okay. So when a Bitcoin node crashes, like a lot of people will tell you, when your Lightning node crashes, you can't receive payments, right? But if your Bitcoin node crashes, even then you can't receive payments, right? So what happens in the Lightning network is that your Lightning your transactions are connected to your own node, right? So if your node, which is used to establish a channel, if it crashes, then you cannot accept payments, you cannot send or receive payments. But with Bitcoin, even if your node crashes, there are other nodes on the network through which you can receive payments. But if your Bitcoin node is connected to your Lightning node and your Bitcoin node crashes, you can't receive payments on the Lightning node as well, right? And not only that, you can be cheated. Somebody can broadcast a revoked commitment transactions, and we've talked about what revoked commitment transactions are previously in detail. So somebody can broadcast, if your Lightning node is connected to your Bitcoin node and your Bitcoin node crashes, one of your Lightning channel partner can broadcast a revoked commitment transaction and steal your funds. And if your Bitcoin node does not come back online before the time lock expires of the HTLC of your Lightning network, then you might end up losing all your funds. So this is another a threat of crashing a Bitcoin node, which is connected to a Lightning node. So this is what the first vulnerability was. Okay, let's look at what the second one is. DOS from very large inventory sets. For each of its peers, a Bitcoin Core node keeps a list of transactions to send to that peer. The transactions in the list are sorted based on their features and their relationships to each other in an attempt to ensure that the best transactions relay fast to make it harder to probe the relay network topology. So every Bitcoin Core node keeps a list of transactions to send to that peer, right? Because if your peer already has received a transaction, there is no point in sending that transaction again to them. And if you've already sent a transaction to a peer, then there's no point sending the transaction to them again, right? So you only broadcast those transactions to your peers which they don't have. How do you know which transactions they don't have? Okay. One indicator could be they sent you a transaction. So there's a certain transaction A which Alice's node sent to Bob's node. Now Bob knows that Alice's node is aware of that transaction A. So Bob's node will not send that transaction A again back to Alice's node, right? That's one way of knowing. The second way of knowing is there's a transaction B and Bob's node sends that transaction to Alice's node. So Bob's node has already sent that transaction to Alice's node. Bob's node will not send it again, right? So one of the way of knowing whether any of your peers have a transaction or already or no is if that peer has already broadcasted that transaction to you, you know that they have that transaction. And if you broadcasted that transaction to them, then you know that they already have that transaction. So there is no point relaying transactions to your peers that already have those transactions, right? So you maintain an inventory of transactions which you know or which you believe that your peers do not have, and you will only broadcast those transactions, right? Now you are connected to multiple peers on the network. Some of your peers might have a transaction, they might not have the other. Some of your peers might have another transaction, they might not have another. So you maintain a distinct inventory for each node, keeping into mind what transactions your peers might have or might not have. Okay, and how do you arrange that inventory? You arrange them on the set of fee rates, right? So the transactions that are paying higher fee, you must broadcast them quicker. Like they must be high priority transactions, because the quicker they are relayed across the network, the quicker they are included in people's mempools, the quicker they are included on the blockchain. So when you arrange this inventory of transactions that you want to send to your peers, you arrange the transactions in the order of fee rates. So the transactions that are paying the highest fee rates should be given a priority in that inventory set. And the relationship to each other, right? The parent should be relayed first and then the child, right? If the child is paying higher fee and the parent is paying lower fee, there's no point relaying the child before the parent, right? Because the child cannot get confirmed before the parent gets confirmed. So there are two things that you look into when you maintain inventory sets that you have to share with your peers. Firstly, you arrange transactions based on the fee rate. The higher the fee rate, the more priority the transaction gets. And the second is their relationship, their topology in the network, right? The parent needs to be broadcasted before the child is broadcasted. However, during a surge of network activity in May 2023, several users began noticing their nodes using an excessive amount of CPU. Developer B10C determined that the CPU was being consumed by sorting functions. Developer Anthony Towns investigated further and fixed the problem by ensuring transactions left the queue at a variable rate that increases during periods of high demand. This fix was released in Bitcoin Core 25.0. So basically, there is a fixed rate at which you can broadcast transactions, right? A node is not allowed to broadcast transactions at its own will, right? There is a limit to which a node is restricted, and only at that limit the node can broadcast transactions. Why? To prevent free relay attacks, to prevent DOS attacks. Because if you allow a node to abruptly relay as many transactions as it wants per second. An attacker can start relaying, can just spin up lots and lots of nodes and start relaying hundreds and thousands of transactions every second and overburden the entire network. So that is why you keep a check on that, and you only allow nodes to relay certain amount of transactions per second. Okay. And now it was now because your the amount of transactions that you are allowed to broadcast to your peers is restricted, right? But your inventory set might grow at a rate faster than the rate at which you are relaying. So you are only allowed to relay to your peers transactions, let's say X transactions per second, but your inventory set is growing at a rate of greater than X transactions per set. So what happens is that you have to invest a lot of computation in sorting these transactions as well, right? Just now we discussed that the nodes have inventory sets which they maintain to relay transactions to their peers. Now they don't randomly relay those transactions. That inventory set is subjected to a certain algorithm, and transactions in that inventory set are arranged in order. In what order? In feed order and topology order. Okay. Now you obviously have to invest computation to arrange the transactions in that inventory set. Okay. And if your inventory set is growing at a very rapid rate, then you have to invest a lot of CPU power to sort those transactions, to perform those algorithms on those transactions to ensure that they are arranged in the order of T rates and network topology. All right. And in May 2023, the network's traffic went up exponentially, due to which a lot of excessive CPU power was being used for these sorting algorithms, right? Because your inventory set was growing up. You were relaying transactions to your peers at a fixed rate, but because there is a high traffic in the network, your inventory set is growing at a high rate, right? So a lot of your CPU is being utilized in sorting the transactions in the inventory rate. Now, how do you bring that down? If your CPU, if your computational power is engaged in sorting those transactions, and it obviously engages your node from performing other activities. It might even lead to your node being crashed. If your CPU is being overburdened, your node might even crash. So how do you keep a track on that? Let's read what the vulnerability is about to get a better grasp of it. All right. As part of transaction relay, Bitcoin Core maintains a per peer. This is the variable m underscore tx underscore inventory to send. So for every variable, you maintain a set of transactions that you have to send to that specific peer, taking into consideration the transactions that you believe that the peer does not already have. Set with transactions that should be announced to the peer. When constructing an inventory message for a peer, the set is sorted by transaction dependency fee rate to prioritize high fee rate transactions and to avoid leaking the order the node learned about the transactions. Before Bitcoin Core version 25.0, when constructing inventory messages relevant still in mempool, not yet announced to us by the peer above the fee filter, transactions were being drained at a rate of 7 transactions per second. So the rate at which you announce transactions to your peers is what? 7 transactions per second. And if any of you attended the last PR review club at Bitshala, then we talked about a PR that talks about increase in investment. Okay, I think in 2023 itself, a PR was opened that suggested that we should increase from 7 to 22 transactions. That PR got closed, and recently another PR is open to increase this number to 14 transactions. But as far as my knowledge is concerned, currently the relay rate is 7 transactions per second. In early May 2023, increased network activity caused the sets to grow faster than they were being drained, right? So you are only allowed to relay 7 transactions per second, but because there is so much of traffic on the network, your inventory set is growing at a rate of faster than 7 transactions per second. And the more your inventory set grows, the more computational power you have to invest in sorting that inventory set in the order of dependencies and fee rate. In early May 2023, increased network activity caused the sets to grow faster than they were being drained, resulting in significant time spent sorting the sets in the peer-to-peer communication thread. Additionally, peers that only listen for transaction announcements but never announce any themselves, commonly referred to as spy nodes, amplified this by having huge sets with transactions they already know that take a long time to sort. It was observed that Sorting took up nearly the complete time spent in the P2P communication thread, which significantly affected block and transaction propagation, as well as keeping connection with peers alive, right? So if your CPU is engaged with sorting your inventory, it has less resources available to perform other tasks. So when the network traffic increased exponentially in May 2023, it was observed that the majority of the computational power was being invested in just sorting these inventory sorts. Okay, and how was that fixed? This was fixed in PR 27610. How was it fixed? By one. Okay, it was fixed in two steps or two stages. One, earlier removing transactions that aren't in the mempool anymore. And two, by dynamically increasing the set drainage rate depending on the size. So the transactions that are not in your mempool were not eligible to be stored in your inventory set. You can only relay those transactions to your peers that are in your mempool. Those transactions which are not in your mempool, you are not allowed to relay those transactions from your inventory set to your peers, which reduces the size of your inventory set, because earlier you were having transactions in your inventory set which were not a part of your mempool as well. But now you're only allowed to keep those transactions in your inventory set which are a part of your mempool, thereby reducing the size of the inventory set. The smaller the inventory set, the less computational power you have to invest to solve the inventory set. That is the first step. And what is the second one? By dynamically increasing the set drainage rate depending on the set size. So up like this, the drainage rate was 7 transactions per second, right? So you were allowed to broadcast 7 transactions per second to your peers. However, when this was static, but then it was made dynamic. Okay, so it depended on the size of your inventory set. If your inventory set grows, then the amount of transactions that you can relay also grows. Okay, so the more your inventory set grows, the more you are allowed to relay transactions to your peers. And once you've relayed a transaction to your peer, it is not a part of your inventory set anymore. So the quicker and the more the number of transactions that you relay to your peers, the lesser or the smaller your inventory set becomes. And the smaller your inventory set becomes, the less computational power you have to invest in sorting the inventory set in order of dependency and high-fee rate. So this is what this vulnerability was about and how it is fixed. To summarize, every Bitcoin core node maintains an inventory set which is unique to each peer. In that inventory set, you maintain transactions which you believe peers do not have, and you intend to relay those transactions to your peers. Okay, now you are only allowed to relay 7 transactions per second to your peers. However, when there is a high traffic on the network, your inventory set grows at a quicker rate and drains at a smaller rate. You're only allowed to relay transactions at the rate of 7 transactions per second, but because there's so much traffic on the network, your inventory set keeps on growing exponentially. And when your inventory set grows up exponentially, you have to invest a lot of computational power to solve the inventory set in order of dependencies and fee rate, which led to an observation in May 2023 that the majority of the CPU was being invested in sorting the transactions in the inventory set. And a fix was made. How was the fix made? The nodes were only allowed to relay those transactions and maintain those transactions in their inventory set, which are a part of their own mempool, thereby truncating the size of their inventory set. And secondly, the rate at which the inventory set was drained, or the rate at which the nodes were allowed to relay transactions, was not static anymore. It varied in accordance with the size of the inventory set. So when the inventory set grows, you are allowed to relay more transactions to ensure that the inventory set shrinks again and comes back to normal, and majority of your CPU power is not invested in sorting the transactions in your inventory set. So yeah, any questions, any observations pertaining this specific vulnerability? Okay, let's quickly cover this. In 15 minutes, let's try and cover the third vulnerability. We have two more vulnerabilities, in fact, right? Let's try and give 5 minutes each to this third vulnerability of Bitcoin Core, 5 minutes to the vulnerability of btcd, and then let's give 5 minutes to the PR, and let's wind it up by 9:05. Cool. So the third vulnerability is title slow block propagation attack. Let's directly read it from here so we can save time. So reading twice. A Bitcoin core treats a block as mutated when, for example, the Merkle root in the header or the witness commitment in the Coinbase transaction doesn't match the transactions in the block. So you have transactions in a block. You hash those transactions. Those transactions are firstly arranged in the form of Merkle tree, which is a data structure that I believe most people are familiar with. Okay, and the root of that Merkle tree is in the block header. Okay, so the Merkle root should match the hashes of the transactions, and if your Merkle root does not correspond to the Merkle tree that you have in the block, then that is considered as a mutated block, and that is an invalid block, and the nodes will reject it. Before Bitcoin Core version 25.0, a peer could clear the block download state of other peers by sending an unrequested mutated block. This was a problem for example, compact block relay. After receiving a compact block and while waiting for a response to get a block transaction request to reconstruct the full block, receiving the mutated block would let Bitcoin Core forget about the compact block reconstruction state. A block transaction response arriving after the mutated block couldn't be used to reconstruct the block. This hindered block propagation. Okay. This problem was a problem for example, compact relay blocks. After receiving compact block and while waiting for a response to get a block transaction request to reconstruct a full block, receiving the mutated block would let Bitcoin Core forget about the compact block reconstruction state. So if you've received a compact block and there are some transactions missing in that compact block, you will ask that peer for those missing transactions, and it takes some time for that peer to send you those missing transactions. In the meantime, if you get a mutated block. In the meantime, if you get a mutated block, uh, Bitcoin Core will neglect or overlook the fact that you are still waiting for that compact block to be reconstructed, right? So your compact block is incomplete. You are waiting for your peer to send you transactions that are missing so that you can reconstruct your block. Now, while you are waiting to reconstruct your block, in the meantime, if you receive a mutated block of the same block index, okay, then what will happen is that Bitcoin Core will overlook the fact that you are waiting for that block, waiting for that block. A block transaction response arriving after the mutated block couldn't be used to reconstruct the block. So you got a mutated block. Okay, you are waiting for to reconstruct your compact block. In the meantime, you received a mutated block of the same a block height. Okay, so let's say you got a compact block of block height 1000. Okay, now there are some missing transactions. You request those transactions from a peer. Your peer is in the process of sending you the missing transactions so that you can reconstruct block 1000. In the meantime, from some other peer, you receive a full block. You receive a full block of the same block index 1000. Now, let's say that block is a mutated block. That block is a mutated block. Bitcoin Core obviously will reject that mutated block, and it will also overlook the fact that you are waiting for your peer to send you missing transactions so that you can reconstruct that specific block. Okay, and even after that, even if your peer sends you the missing transactions, you will not be able to reconstruct your block. Okay, so when you're waiting to reconstruct your block, if you receive a mutated block, that process of reconstructing your block gets aborted. If that mutated block is invalid, the process of reconstructing the block gets aborted, and then you have to start that process all over again. This was fixed in PR 27608 by making sure that a peer can only affect its own block download state and not the download state of the others. Okay, so basically what this means is that even if you get a mutated block and after that mutated block you get this block transaction message, this block transaction message will still be valid and you can reconstruct your block using this block transaction message. This is what this means in short. So receiving a mutated block does not invalidate your block transaction message. You can still reconstruct your compact block with the previous get block transaction message which you send to that peer, and you don't have to again initiate the process of reconstructing the block. All right, because of time constraints, I won't go into too much of detail of this PR. I believe I've covered it adequately. But if still there are any questions, anything that anybody would like to ask about this specific vulnerability, please go ahead and do so. All right, where did I go? Fine. Now we've covered all three vulnerabilities of Bitcoin Core. The first being about a remote crash vulnerability, the second one being about inventory sets, and the third one being about slow block propagation. Now let's talk about a vulnerability in btcd. As announced in last week's newsletter, Antoine François and Nicholas Gerger disclosed a consensus failure vulnerability affecting the btcd full node. We discussed this last week. In legacy Bitcoin transactions, signatures are stored in the signature script field. However, the signatures also commit to the signature script field. It's not possible for a signature to commit to itself, so signers commit to all of the data in the signature script field except for the signature. Verifiers must correspondingly remove the signature before checking the accuracy of the signature commitment. So in Bitcoin, or basically in cryptography, digital signatures are used to send messages, right? In Bitcoin, what are those messages? Those messages are transactions. So we use digital signatures to sign transactions. Now, a signature cannot sign itself. A signature cannot sign itself. However, we know that a signature is a part of a Bitcoin transaction. Just now we discussed that digital signatures in Bitcoin are used to sign transactions, but signatures themselves are a part of a transaction and a signature cannot sign itself. Signatures are a part of the script sig. So what do? You remove the signature from the transaction and then you sign the transaction. And when the person is validating that signature, they strip the transaction of the signature and then they validate the signature. Bitcoin Core's function removing signatures, find and delete only removes exact matches of the signature from the signature script. Okay, so there is a function in Bitcoin Core, find and delete. What does it do? It finds the signature in a transaction from the script sig field and removes that signature. And once the transaction is stripped of that signature, then it validates the transaction. Okay, but the catch here is that Bitcoin Core will only strip the signature by an exact match. We know what an exact match is, right? So Bitcoin Core takes the signature and searches for that string, that exact string of the signature in the script sig field, and strips off the signature from the script sig field and then validates the signature against the transaction after it has stripped off the signature from the script sig field. The function implemented by BTC remove opcode by data removed any data in the signature script which contained the signature. Okay. So the function that is responsible for doing this in Bitcoin Core is called find and delete, and the function that is responsible for doing this in BTC is remove opcode by data. What's the difference? In Bitcoin Core, this find and delete message will find the signature in the script sig field by exact match. It will exactly look for that signature and only strip off that part of the signature. Whereas in BTCD, it will also strip off if there is any pendant data to the signature. If there is anything before the signature, if there is anything after the signature which is appendant to it, it will remove all of that. Okay, this could be used to cause BTCD to remove more data from the signature script than Bitcoin Core would remove from it, respectively verified the commitment, leading one program to consider the commitment valid and the other invalid. Now, what could happen is that uh, Bitcoin Core will consider that transaction to be valid and BTCD would consider the same transaction to be invalid, right? Because Bitcoin Core is using exact match to strip off the signature from the script sig, whereas BTCD is not using exact match. It is removing any data in the signature script. It is removing any data in the signature script. It is not using exact match. Okay. So in that situation, it might happen that a signature might get validated by Bitcoin Core and Bitcoin Core might consider that transaction to be valid, but the signature might be invalidated by BTCD, and due to which the same transaction might consider to be invalid due to BTCD. In BTCD, what would happen is that the transaction if that transaction is included in a block, Bitcoin Core will consider that block to be valid, and BTCD nodes will consider that block to be invalid, which could lead to a chain split. And this is a very serious issue. Any transaction containing an invalid commitment is invalid, and any block containing an invalid transaction is invalid, allowing consensus between Bitcoin Core and BTCD to be broken. Nodes that fall out of consensus can be tricked into accepting invalid transactions and may not see the latest transactions the rest of the network considers to be confirmed, either of which can result in a significant loss of money. Consorts and Gerger's responsible disclosure allowed BTCD maintainers to quietly fix the vulnerability and release version 0.24.2 with a fix about 3 months ago. Okay, so I believe the fix obviously will be that even BTCD now strips off the signature using exact matches. So that a transaction that is considered valid or a digital signature that is considered valid by Bitcoin Core is also considered valid by BTCD, and a signature that is considered invalid by BTCD is also considered invalid by Bitcoin Core. All right. So this is what this vulnerability was, that In Bitcoin, the digital signatures are used to sign the transactions, but a signature cannot sign itself. So you remove the transaction. So you remove the signature from the transaction and sign the transaction. Okay. And even while validating, you strip the signature and you validate. But the process of stripping of that signature was different in Bitcoin Core and different in BTCD. Bitcoin Core would use exact match to strip off that signature, but BTCD would strip off any signature that is in the signature script, which would lead to a transaction being valid, which might lead to a transaction being valid in Bitcoin Core and a transaction being invalid in Bitcoin in BTCD. Thus, Bitcoin Core might consider a block to be valid and BTCD nodes might consider that same block to be invalid, which could lead to a break in consensus and a chain split between the clients running these two softwares. It was fixed. How was it fixed? It was fixed by, I believe, prima facie, I believe it was fixed by BTCD also deploying the same mechanism. BTCD also using exact matches to strip off signatures while validating transactions. If there are any questions pertaining this, please feel free to ask. Else we can go to the PR and try and cover the PR in 5 minutes. Just discuss over it for 5 minutes. Anything to say or share? Cool. If nothing, right, cool. Okay. So we will go to the Bitcoin Core PR Review Club. This is a monthly segment, and this week the PR that we have is called Add Get Often Transactions. Add Get Often Transactions is a PR by TDB3 and adds a new experimental RPC method named Get Often Transactions. Since it is intended primarily for developers, it is hidden. This new method provides the caller with a list of all current often transactions, which can be helpful when checking often behavior scenarios, example in functional tests like P2P often handling.py, or for providing additional data for statistics visualization. All right. So we know what often transactions are, right? We've talked about them in various preceding sessions. What often transactions? Often transactions are transactions that have missing inputs. Okay, that either don't have parents or their parents are missing. Okay, so it is possible that your node might see the child transaction before the parent transaction. Your node might see a child transaction before the parent transaction. Now, if your node sees a child transaction before a parent transaction, your node cannot validate that child transaction, right? Because you need to know whether the parent is valid or no for the child to be valid. If only if the parent is valid can the child be valid. If you have access to the child but you don't have access to the parent, you cannot validate the child transaction because the parent is missing. What do you do in such a situation? Then you keep these transactions in orphanage. So there is a place, quote unquote, place in your node known as orphanage. You keep these transactions in the orphanage. And every time you see a new transaction, you see if this transaction, if the parent of that orphan transaction, which you have in the orphanage, and if it is, then you validate the parent transaction and the child transaction. Okay. And I think the limit is 100 transactions. You can store 100 transactions maximum in your orphanage, and the maximum amount of time for which a transaction can remain in the orphanage is 20 minutes. Till 20 minutes, if a transaction has been in your orphanage and you don't find its parent transaction, you flush it out of your orphanage, right? And if you have 100 transactions already in your orphanage, then more transactions cannot enter your orphanage. Now a new RPC is being introduced. We all know what RPC calls are, right? We've all used the terminal. So get blockchain inflow, get network info, get raw transaction, get transaction, create raw transaction. All of these are RPC infos. So a new RPC call has been introduced called get often transactions. Okay. What's peculiar about this RPC call? This is not available or accessible to end users. Okay. So if you want, like if you open your Bitcoin terminal, right? And you run a command Bitcoin hyphen CLI hyphen help. What happens is that you get a list of RPC calls, right? This RPC call will not be listed. There are certain RPC calls which are specific for the developers. Those RPC calls are not a part of the help command. So if you open your Bitcoin terminal, you type Bitcoin CLI RPC. If you basically build and compile this PR, okay, and you start running a Bitcoin core node pointing to this specific branch, the branch with this PR as your head, and you run Bitcoin CLI help, you will not see this transaction in the list of transactions. So you will not see this RPC, I'm sorry, in the list of RPCs. There are certain RPCs which are specific for the developers. Those RPCs are not given access of to the end user. So if you type Bitcoin CLI help, you will not see this RPC. You have to know that this RPC exists as a developer. What this RPC will do is it will give you information pertaining often transactions. Okay, so basically this is what this PR does. If you have often transactions, if your node sees a child before it sees a parent, it cannot validate the child. So what will it do? It will keep that child in a place called orphanage as an orphan transaction. That orphanage can contain maximum 100 transactions, and a transaction can be in that orphanage maximum for 20 minutes. If you want to recreate information pertaining those orphan transactions, a new RPC call has been added by the name of get orphan transactions. So you can run Bitcoin CLI space get orphan transactions. You will get information pertaining those transactions. And what's peculiar about this RPC is that this is not available for the end users. Meaning, if you type Bitcoin CLI help, this will not be printed onto your terminal. You have to know as a developer that this transaction exists. Let me see if my I was looking into this in the afternoon. Let me see if we can see that value of maximum transactions. Or is it in the terminal? Okay, cool. Anyhow, let it be. Yeah, so basically its value is 100. Uh, let's just read the answers quickly in the next 2 to 3 minutes, and at 9:10 sharp we can uh, call it a session. What is an orphan transaction? At what point do transactions enter the orphanage? An orphan transaction is one whose inputs refer to unknown or missing parent transactions. Transactions enter the orphanage when they are received from a peer, but they fail validation, which takes missing inputs and process the message. Right? So if your node sees a transaction whose inputs are missing, meaning its parents is missing, the validation of the transaction fails, and that transaction is considered as an orphan transaction because its parents or its inputs are missing. What command can you run to get a list of available RPCs? Bitcoin CLI help provides a list of available RPCs. Note, since get orphan transactions is marked as hidden as a developer only RPC, it will not show up in the list. If an RPC has a non-string argument, does anything special need to be done to handle it? Non-string RPC arguments must be added to the VRPC convert params list in source RPC client CPP to ensure proper type conversion. This is not for the end users. This is for people who contribute to Bitcoin Core or any Bitcoin client for that matter. What is the maximum size of the result from this RPC? Is there a limit to how many orphans are retained? Is there a limit to how long orphans can stay in the orphanage? The maximum number of orphans is 100. Default max orphan transactions. Okay, so there can be 100 transactions maximum in the orphanage. At verbosity 0, each TX ID is 32 byte, a binary value. But when hex encoded for the JSON RPC result, it becomes a 64 character string. Okay, so basically transactions, Bitcoin transactions, often transactions are represented by a 32 byte TX ID. Okay, but if you want to view them in JSON format, then they are first to be encoded in the hexadecimal equivalent, which is 64 characters. So you can either represent open transactions in the form of TXID, which will be 34 byte, or you can represent them in the form of hexadecimal outputs, which will be 64 bytes. This means the maximum result is approximately 6.4 KB. That is 100 TXIDs of 64 bytes. At verbosity equals to 2, the hex encoded transaction is by far the largest field in the result. So for simplicity, we'll ignore the other fields in this calculation. The maximum serialized size of a transaction can be up to 400 KB in the extreme impossible case that it consists only of witness data, or 800 KB when hex encoded. Therefore, the maximum result is roughly 800 MB. So the maximum result of this RPC can be 800 MB. Since when has there been a maximum orphanage size? The max orphan transaction variable was introduced back in 2012 already in commit such and such. Using the get orphan transactions RPC, would we be able to tell how long a transaction has been in the orphanage? If yes, how would you do it? Yes, by using verbosity equals to 1, you can get the expiration timestamp of each orphan transaction, subtracting the orphan TX expired time. So if you want to know when the transaction will expire, because like I told you, an orphan transaction can only exist in the orphanage for 20 minutes. If you want to know how much time is remaining for it to expire, while issuing the command, you can use verbosity 1. It'll show you how much time is remaining for that orphan transaction to expire. Using get orphan transactions RPC, would we be able to tell what the inputs of an orphan transaction are? If yes, how would you do it? Yes, with verbosity equals to 2, the RPC returns a raw transaction hex which can be decoded using decode raw transaction to reveal the inputs. Okay, so if you use verbosity 2, and if the inputs of a raw of an orphan transaction is detected, then it will show you what those inputs are. Anything? Yeah, just one thing I wanted to discuss or say is that testnet 4 is now available for Bitcoin Rust. We've talked in detail about testnet 4. It has been activated on Bitcoin Core 28.0. It's also available now for Bitcoin Rust. That is all from my end. We covered 3 vulnerabilities for Bitcoin Core, one for BTCD, one PR, and one code and documentation change. That is it. That's what we can cover for the week. If anybody has anything to share, any questions, please feel free to go ahead and do so. And if nothing, then it's curtains from my end.